Welcome back to part 2 of our explainer on hazardous area equipment selection. Let's skip the long preamble and drop right into the rest of the toolkit, those other specialized X protection types.
Okay, let's dive into this. If you caught part 1, you'll remember we talked about keeping gas out with air pressure using XPEP, or pressurization. We saw how in Zone 1, a pressure failure triggers an automatic disconnect, while in Zone 2, it just fails with an alarm. That set the stage for how we physically separate ignition sources from explosive gases. Now let's finish the toolkit.
Today, we're looking at 4 more protection methods. The goal is exactly the same, right? Keeping things from exploding. But the physical realities of how they actually pull that off, completely different. We are moving way beyond just thick metal boxes and air pressure.
First up is XM, which stands for encapsulation. With this method, your sparking parts get embedded directly into a solid resin block. It literally denies the hazardous gas any physical contact with the ignition-capable part at all. You'll usually see this rated for Zone 1 or Zone 2, and honestly, it's a fantastic choice for small sensors, solenoids, or circuit boards. Basically, anywhere a full metal flame-proof enclosure would just be wildly impractical or way too heavy.
All right, time for a quick check. I want to test your assumptions on how we apply these methods out in the real world. Here's a high-stakes question for you. Let's say a portable hand tool needs X protection for use in Zone 1. Could it be protected using oil immersion, which is known as XO? Think about it for a second.
The answer is a hard no. According to the IEC standards, XO is strictly prohibited on portable or transportable equipment, full stop, regardless of the zone. And the reason makes perfect sense. Tilting or spilling risks make oil immersion completely unacceptable for anything that moves. If it's not permanently fixed in place, oil immersion is entirely off the table. You'd need to pick a different method entirely, like encapsulation or intrinsic safety.
Now, what's really interesting about this slide is how we can contrast XO with our next method, XQ. Both act as physical barriers against spark propagation, but they use very different mediums. XO, as we just discussed, submerges live parts in protective insulating oil, and remember, that's for fixed installations only. XQ, on the other hand, buries live parts in quartz sand or a fine powder. If a spark actually happens, that sand bunker physically prevents the flame from propagating outward.
That brings us to XN, known as non-incentive or non-sparking protection. This is essentially your lightest touch protection method, and that's because it's matched to the lowest likelihood risk area. It is exclusively for Zone 2 environments, places where an explosive atmosphere is pretty unlikely to occur, and if it does, it's only sticking around for a short time. XN relies on non-sparking component design, enclosed break switching devices, and sometimes restricted breathing enclosures. It's basically a catch-all ensuring that during normal operation, the equipment just isn't capable of igniting a surrounding explosive mixture.
And this brilliantly illustrates our main point here. Think of these abstract IEC codes as distinct survival strategies on a battlefield. XD, flameproof, that's the knight's armor. It takes the hit and contains the blast. XE, increased safety. That's the soldier keeping a careful distance to prevent the spark from even happening. XQ, powder filling, is literally hiding yourself in a sand bunker. And XN, non-sparking, well, that's the lookout, just evading the danger zone entirely, which is exactly why it's only allowed in the lower risk Zone 2.
All of this builds into our master matrix. This is your ultimate mental screenshot of all 8 strategies we've covered across parts 1 and 2. You can clearly see how each method pairs with a specific physical strategy. We've got containment, prevention, energy limiting, separation, resin, oil, sand, or just pure avoidance. And crucially, it maps them directly to their zone suitability. This right here is the entire toolkit for safely deploying electrical equipment in explosive atmospheres. Equipment selection, done.
But here's the catch. Every single one of these protection methods, the entire toolkit, fails if the cable feeding it is wrong. You can perfectly match your equipment to the zone, use the right protection method, do everything completely by the book, but if the wiring and the glands aren't compliant, they become the Achilles heel of the whole setup. Let's make sure the wiring holds up its end of the deal. In our next explainer, we'll dive into cable specs and gland selection to secure the whole shebang. Thanks for joining me, and stay curious.